Yeah.
the entire thing.
Exactly.
And then you get back and you're like, oh, it's recording this.
So we'll call this take 2. Yeah. Because I forgot to hit record in the first class. But that's okay. I was all jacked up in the first class. Okay? So the first Starbucks opened the net. So what I would like you to do now is I would like you to use this data and I would like you to create a scatter plot based off of this data with the year representing the number of years from 1988. So that means, like we were doing yesterday, I believe we did a scatter plot with, or no, that was last week when we did the scatter plot with San Jose's population. We set 1988 as year 0, okay, to bring our numbers down a little bit. Okay? So again, use that as year 0. So if you could create a scatter plot right now, that would be awesome. Awesome. All right, so we're going to add in our lists and spreadsheets. I'm going to go with Y for years. Okay. I just got to grab a sheet here that tells me what it is. Actually, it's faster over here on the computer. Y with years, and then I'm going to go 0, 2, 4, 6, 8, 10, 12, and 14. Then I'm going to go with N for number. If you wanted to go with a full word there, that's fine. Just remember you can't have a space in it. I like to go with just single letters just because then it's easier to type in. And that's going to be 33, and then 84, and then 165, and then 425. And then people started really liking coffee, so then we went to 1,015, big jump that year. And then another huge jump, and then another ginormous, a doubling almost of it. And then another huge jump because now people are addicted. Okay? It's Starbucks. Starbucks is like a drug. I get it. Okay? All right? So there's our scatter plot, or there's the data for our scatter plot. Now we are going to make a scatter plot. Now, there are 2 different ways to make a scatter plot. I will show them both to you right now. Okay? One way is the data and statistics method, okay? Where you have this randomly thrown on stuff, and then you start and you click to label your variables, and that's going to be the number of stores, and then we click to add our variables, and that's going to be the year, and then whoa, there's a scatter plot. Okay? Like it, works, okay? I'm all for it. But my favoriteest one is I'm going to add a graph. And in the graph, I can do what type of graph it is, and that is a scatter plot. And then I can say that I want my X values to be my years, which was Y, and I want my Y values to be my number of stores, which was N. But then the downfall is I can't see anything. So I have to go through and I have to adjust my window. And so I don't need to see anything on the left, but I do like to see my axes. I figure let's go out to 20 years and let's go by 2 because our graph on our piece of paper was by 2s. My Y's, I need to get all the way up to at least 5,800. So I'm going to go negative 500, and I'm going to go up to 6,500, and I'm going to go by 500s. So there is the scatter plot. Again, this scatter plot is the same as that scatter plot, just in a different function on the calculator. Again, personal preference. What we're doing, we can do in either way. Okay? Okay? All right. So there is the scatter plot. Boom. Done. What type of function would seem to best model the growth of the bucks that are starred? And what type of function do we think that is? Say it loud and proud. Exponential. It's not linear because the rate is not always changing at the same time. The change is changing, so that I would feel that is exponential. Yes, ma'am.
Do we always have to use exponential, or can we use like cubic?
Well, I mean, what do you think?
Well, I think cubic is better with like the correlation coefficient.
Okay. Okay. Well, for right now, let's go with exponential because that's what we're talking about. Wink, wink, nudge, nudge. Okay? All right? Okay? So I would go here with exponential. But no, sometimes it might be different. Okay? Okay? So there we go. Now, what I should do... Love... Oh, that's kind of loud. Sorry about that. Forgot I was right next to the microphone. Hey now. Okay. All right. So we're done with that. Let's go to the next question. Question number 3. Using the model n of t equals a times b to the t power, what I would like you to do now is I would like you to come up with an exponential model to fit the data that we just had. Okay? Go for it. For all of us, what is our a value? 33, because it's the value when t is equal to 0. So for all of us, a is 33. Now I want my exponential model to be in this form right here. Correct? So I'm going to have to use another point. How many people chose 1990 as their point? Okay, and that's fine. Okay, all right. So if we chose 1990 as our point, then I'm going to say here that 84 is equal to 33 times b to the second power. Okay. One of the reasons that you would probably want to choose that one is because it's the first point. You only got to take the square root because you divide both sides by 33. And then you take the square root. And so I got to get a calculator. Here it is right there. So the square root, all clear, square root of 84 divided, oh, tap the brakes, got to put that in parentheses. Square root of 84 divided by 33 gets me, and I get a b value here of 1.59545. Gets me my b value. Okay? Now, we rounded it. And yesterday we realized that when we round it and then we go to, use our model, that we don't get exact numbers. We get close numbers. So on the graphing calculator, let me show you how to make it so that it's exact. Okay? So on this one, I said that I had to take the square root of 84 divided by 33, and that was my 1.59545 number. Okay? But I then am going to store that number as my b. Come on, as my b. There's my b. Okay? So there is that number stored in my calculator as my b. Now when I use that, it's going to be exact. So if I said 33 times b to the second power, I get 84. Okay? Which is what I need it to be. Now, here's where we're going to go back and we're going to check it on our scatter plot. So I'm going to put my function in as 33 times, now here's the kicker. I'm going to use b as my base. It's bolded, it's stored on the calculator as 1.59545, but not rounded, and then take that to the x power. Okay? So I can do that, and I get that function right there. What do you think of that function? Does it fit our data? Not really. Okay? Not really, not the best. So if I was on here, I would go in Menu, Analyze, Plot Function, same thing. 33 times b to the x power, again, gets me the same thing. Okay? Not very good. The reason that it's not very good is because we took, and actually let me go back to, whoa, not to there, to here. the reason that it's not very good is because we took 2 decimal points that were right next to one another. Okay? So we took, or not 2 decimal points, excuse me. We took 2 data points and we put them right next to one another. Okay? So it didn't necessarily work out the best for us. Okay? So let's try and go a little farther out with our 2, a little more spread on our data points. Okay? So let's try this one. So that would be 2, 4, 6, 8, 10. I think 10 might be a better one to try. Okay? And so the data point 10 years out is going to be 1,886 is going to equal 33 times b to the 10th power. Actually, let me move all this stuff over. Move that one over too. Move all this stuff over there. And then I can move this up here. Okay? And so then I'm going to take now my b value here is going to be the 10th root of 1886 divided by 33. Okay? So that's going to give me a b value of 1886 divided by 33 raised to the 0.1 power 1.49866 power. Okay? Now, here's a cool thing about the graphing calculators is if I go into my calculator page and I change the value of b by making it be, whoa, tap the brakes, by making it be the 10th root of 1886 divided by 33, and I store that right away as b, okay, it looks goofy, but it really is, oops, let me go escape on that, oops, yeah, okay, and then let me go there, okay, so that's where we got it from, okay. Now, what it automatically did for us is it changed our function for us, okay. Because we typed our function in as b, it changed the way our function looked on it. So, does that fit a little bit better? Yeah? Okay. I would concur that that fits a little bit better for us. Okay. So, do you want to use that one or do you want to go out to another data point? Out one more? Okay. So, if we go out one more, then we would be taking the, oops, not the natural log. We would be taking the 12th root of 3501 divided by 33, and I would want to store that as b. So that would be that one then, and then looking at my graphs, little bit better? No? Other one better? The 10th one? You make the call. 10th one or 12th one? 10th? Okay. All right. So we'll go back to the 10th one then. So I need to go back here and I need to, one more. Highlight that and hit enter there. So then now that's our 10th one. Okay? All right. So that's the one we're going to go with. All right? So that means that our function then is 33 times 1.49866 to the t power. Okay? Now, next question says, using that exponential model, find the projected number of Starbucks in 2004. How many Starbucks will there be in 2004? Or what year, I should say, is 2004? 16. Okay, so we need to find n of 16. So that is going to be 33 times 1.49866 to the 16th power. Or simply put, I can go to my calculator page and I can say, because it's in function number 1, I can do f1 of 16 and I get, whoa, tap the brakes here, escape. Oh, can I go back up? No, maybe not. Oh, I thought I could go, so let's go like this then. There we go. Okay. I get 21,367.7. Logic tells me, can I have 0.7 of a Starbucks location? No. So we could go 21,368. Okay. There. Okay. Because really this is 21,367.7. Can't have that 0.7 of location, so we could round up or round down there. Whatevs. Okay? Using our exponential function, find when the Starbucks will reach 11,000. So that's going to equal 33 times 1.49866 to the t power. What's the first thing that I'm going to do there? Divide both sides by 33. Uh-oh. Now what? My variable is up in the exponent, right? So we got to do logs. So quick recap here. If I've got the base of an exponent, and that equals my argument. Okay, get to talk like a pirate every once in a while. Okay, then that is the same as log with a base of my argument equals my exponent. Okay, so this really means log base 1.49866 of 11,000 divided by 33 equals t. Okay? Now, how do we type that into a calculator? Well, if you have a graphical TI Nspire one, you use the log key. Okay? And our base here was b. Our argument is 11,000 divided by 33. And that tells me that in 14.3588 years, there will be 11,000 Starbucks. If you are using a non-TI Nspire calculator, you've got to use change of base formula, which is I take the log and I leave the base empty. Divide that. There's my argument. Then I divide that by the log of my base. Again, leaving the base blank. This is called change of base formula. And there's that one. Okay. You could also have gone natural log there and gotten the same thing. Okay. So that tells me that it's going to be in, or t here is equal to 14.35, what do we say? 88? 88 it says, yep. So that to me says minus 14 times 12. That to me says January, February, March, April. Sometime in April of what year? April of what year? It's the 14th year, right? From 1988, so that would be April of 2002. Yep. Okay. Whoa, hey now, virus threatened protection. So wait, no, nothing. See? No viruses. It's Teacher Appreciation Day. Hold on, we got 30 seconds to go, I promise. Okay? All right? All right, so above we determined that according to the exponential regression model, the projected number of Starbucks in the year 2004 would be what? What did we say? 21,368, right? But we now have added data. So the added data we have there is that in 2003 there were 7,200, and in 2004 there were 8,300. Add these values to the scatter plot. Okay, so now I've got to go back into here. Come on now, there it is. So I got to go back into here, and I've got to add in year 15 was at 7225, and year 16 was at 8337. So now when I go to my scatter plot, now I've got to adjust my window a little bit, okay? Because now I need this to go up to, we'll call it 9,500, okay? So there's that. Now, what can you tell me about adding those two data points in? So my model is not necessarily very good, but also from our data that we collected, we said that this one should be at 11,000, which would be up and about here, okay? And then the other one should be 21,000, which is way up here by the ceiling, okay? So what's happening to our data? Our actual data, the rate is actually slowing down a little bit, right? So it's not necessarily continuing to grow in that exponential fashion, which is where we pick up with logistics tomorrow. Okay? Have yourselves a great, grand, and wonderful day, and happy Teacher Appreciation Day to you all.